This video is going to review parametric functions and how we work with them in calculus. I'm going to focus on all of the derivative applications in this video and then look more at integral applications and some of the pre-calculus stuff in other videos. So this focuses on what the derivative, how we find it, and what it does for us as far as applications. For the first question up here, it's a particle motion question, and we have the parametric equations that describe the particle motion. They do remind you in this problem that with particle motion we are only working with positive values of t. We want to find the slope of the tangent to the path of the particle when t equals 4. So when we're finding slope, we just want the first derivative, and if you remember, the first derivative is dy dt over dx dt. So I tend to find them in that order. So I go to my y equation. The derivative of y in terms of t would be 2e to the 2t minus 7. And then the derivative of x in terms of t would be 6t minus 19. And they give us a particular value of t. They want to know what the slope would be when t is 4. So I'm going to put 4 in. 2e to the 2 times 4 is 8, minus 1 is 7. So 2e to the first, or 2e, over 6 times 4 is 24, minus 19 is 5. So here's our slope. In most situations, you're going to leave your answer like that. The only time you would go to your calculator and figure out the decimal is if it's a multiple choice question and they are asking for your answer to be in decimal form. Other than that, I would leave it there, and then you don't have to worry about accidentally punching something in your calculator wrong or not rounding to the right digit. Next question is also a particle motion question, and it is something similar to what we had done in class. We have parametric equations, x and y, that you see. Again, it reminds you particle motion can't be negative, looking at time bigger than 0. We want to know in the first question, when the time is 1, is my particle moving right or left? So we talked in class that the horizontal motion, the moving right or left, is related to the derivative of x, because x is that horizontal component, that piece that talks about how it moves to right and left. So when we look at our x equation, if we look at the derivative of x, which we call dx dt, we get 2t minus 4. This is the equation that will describe the motion of the horizontal motion. I want to know at 1, so I'm going to put 1 in. I get 2 times 1 minus 4. I get a negative value. Because this value is less than 0, we say that my particle is moving to the left. On an AP test, when they ask something like this, when you have to justify or it'll say explain, all you have to write is that dx dt is less than 0 at time, marker's breaking up on me, 2. You don't even have to show what you get. Then, for example, you don't have to say that you get a negative 2. All you have to say is that you get a negative number. If you plug it in and you get a positive number, that tells you that your particle is moving to the right. We have not talked about vertical motion, vertical component. We'll get more into that when we talk about vectors, but you should at least understand the horizontal motion for this quiz. For the speed of the particle, this formula for speed of the particle, and it is a formula that you should know, it is the square root of dx dt squared, that horizontal component squared, plus dy dt squared, all under the square root. A lot of it is done either in your calculator or just leaving it in exact form, which is what I'm going to do with this one. So dx dt, we already found, is 2t minus 4, so it's going to be the square root of 2t minus 4 squared. Dy dt, the derivative of y in terms of t is 1 over t, so I'll have 1 over t squared. Now I'm going to plug 3 in. So when I plug 3 into the first piece, I get 2 times 3 is 6, minus 4 is 2. 2 squared is 4, so I have the square root of 4. When I put 3 in the other equation, I get 1/3, and 1/3 squared is 1/9. You're not going to usually see your answer left like this. A lot of times a question like this would be a multiple choice type question. So let me show you what they would do with multiple choice if you aren't allowed to use a calculator. If you are allowed to use a calculator, obviously you can just punch it in and see what you get as a decimal. But my guess is a question like this would probably be a non-calculator question. So what they're going to do is they're going to get a common denominator. So instead of 4, I'm going to write it as 36/9 plus 1/9, which is the square root of 37/9. And just from seeing a lot of questions, I can pretty much guess that the correct answer would be the square root of 37 over 3, because the bottom was a perfect square, so they would take the square root of it. The top is not, and you'll never be asked to do anything further with 37 if you're not allowed to use a calculator. Keep in mind, for speed, you have to always end up with a positive result. Speed doesn't have a direction. There is no negative. And when you're taking things and squaring them, you'll never get a negative, no matter what you're plugging in for t, for time. Next question, just as a quick recap of how we find the first and second derivative. We've already found the first one once, so I'll just go through that one more time. Then we'll also review how do we find the second derivative. Your questions with the second derivative, they may ask you to plug a value in for t. You will not see questions about concavity, even though we know that's what the second derivative does. The AP does not ask anything about concavity. They will only ask you to find the second derivative with parametric equations and then possibly plug in a particular value for t into that second derivative. So first we're going to take the derivatives. So we know the first derivative is going to be dy dt over dx dt. I usually start by writing that. And then I'm going to go off and look and see what my dy dt is. It is going to be 4t cubed plus 6t. And then my x, the dx dt, would be 2t. Because I have to go further, I'm going to simplify this. If I don't have to take a second derivative, I'm not going to worry as much about simplifying, but I need to work with something as simple as possible to go further. So I'm going to pretzel this. When I do that, I get 2t squared plus 3. That's the cleanest result for my first derivative. Now I could go further and say, okay, what happens if t is 2 or if t is 3? Or I could even have a negative t here because we're not dealing in a context of a particle motion. In this question, all it wanted was the derivative. Second derivative, when you're asked to find the second derivative of parametric equations, just kind of do a recap of what it is. You have to take the derivative of what you just found. So the notation for that, I'm going to put the notation and then describe it. It's the derivative in terms of t of what you just found, your dy dx, over the derivative of the x piece, of the x component. So for this, I will look at what I just found here as dy dx. When I take the derivative of that in terms of t, I get 4t. Divided by my original dx dt, which was this piece, so I get 2t. And here's a situation that we actually saw show up at least once or twice in class when your second derivative actually ends up being a constant. Meaning if I would have said, well, what's the value of the second derivative at t equals 5? Well, it would be 2. If t equals 10, it's still 2. My second derivative is not variable. It is not changing. It is constant. Next thing we're going to be asked to do is tangent line. You're going to see a set of questions exactly like this on your quiz, getting practice writing a tangent line and then answering questions about different types of tangent lines, horizontal tangent lines and vertical tangent lines being the ones that show up the most. So we're given our parametric equations. We're going to write our tangent line equation at 2. First thing I need is the slope, so I'm going to find that derivative again, dy dt over dx dt. So dy dt is t squared minus 2t minus 3. It's nice to kind of write this all out because I know even when I'm done with this part, it's going to really help me for the next two questions, knowing my derivatives. Dx dt is 6t. We want to know, first of all, about the slope, so I'm going to plug 2 in. When I plug 2 in to my derivative, I get 4 minus 3, so I end up with minus 3. And when I plug 2 into the bottom, I get 12. So my slope is negative 3 over 12, or I can write it reduced as negative 1/4. Now I'm going to look at the coordinate, because to write a tangent line I need a slope, which I have, and I need an x and a y, and right now I just have the t value. So I'm going to have to plug that in here. If I plug 2 into the top equation, I get 2 squared, which is 4, times 3 is 12. 12 minus 4 is 8. And then if I put 2 in the bottom one, this one's going to be a little messier with a fraction. 2 cubed is 8, so I have 8 over 3 minus 4 minus 6 plus 1. Which is 8/3 minus 10 plus 1 minus 9. I'm going to get it all in thirds, so I have 8/3 minus 27/3. So I get negative 19/3. Not the prettiest y coordinate, but I'm still going to put everything in point slope and not have to worry about too much simplifying. So my tangent line equation, y minus 19 minus a minus, so plus 19/3 equals my slope, negative 1/4, x minus 8. And unless they actually ask you in a multiple choice question to rewrite it, get it into maybe a standard form or a slope-intercept form, I'm going to stop. I'm going to leave it in point slope form unless I have to rewrite it. It's just simpler to work with it like that. Next question wants to take the same parametric equations but asks when would the curve be horizontal. Horizontal means that the derivative is 0, which looking at the way we define the derivative In order to get that to be 0, that means it's when dy dt equals 0. So I'm going to set dy dt, which was, I'd already found, as t squared minus 2t minus 3 equal to 0. This factors very nicely. T minus 3, t plus 1. So I get t values of 3 and negative 1. It is okay to get a negative value here because we are not looking at particle motion. This is just a tangent line to a curve. So I'm going to leave both of those. Some questions will ask you to go further. They'll actually ask you for the x and y that corresponds to the t. What we're doing for that is we're taking each t that we find, so we find that t is 3, putting them back into my original parametric functions to figure out what x and y is. So you will see that at times as well, but it's nothing more than just plugging in and getting coordinates. In this case, we would have two coordinates. We would have a coordinate that's formed when we put 3 in, and we'd have a coordinate that we get whenever we put negative 1 in. And then the last part of this question wants to know, when is the tangent line vertical? Vertical means the bottom will be 0 because we have an undefined slope. So this is saying, when does dx dt equal 0? This one's even simpler because dx dt was just 6t, and the only time that's going to equal 0 is when t equals 0. And again, it can go further and say, well, what's the coordinate? What's the xy? A lot of times you'll see it written like that. What's the xy coordinate that gives me a vertical tangent line? So then I would take that 0 value and put it back into the original parametric equations. This would be very easy because t is 0. If I put it into x, I would get negative 4. If I put it into y, I would get 1. So I would say it happens at the point negative 4, positive 1. And actually, that's the last piece of this video. This is looking at the pre-calculus, so we're going to stop here. That takes you through all of your derivatives. You should be able to derive the first derivative and the second derivative. You should be able to use the first derivative the most. You should be able to use the first derivative to help you figure out tangent line equations, determining when the tangent line is horizontal and vertical, determining if a particle is moving right or left, using it to find the speed of a particle. And the second derivative is a little more limited. You should be able to find it, and then you should be able to use it just to plug in particular values of t into that second derivative, but it won't go further into concavity or any other type of application.